You know, when we send missions deep into space, we're not just sending people and equipment. We're sending an artificial brain, an AI, that has to make critical life-or-death decisions all by itself. And this is where some really fascinating new research comes into play. It's all about how we can prune that AI brain, kind of like a gardener, to make it not just faster, but way smarter and more reliable.
Okay, I want you to picture this. You're an astronaut, you're out near Mars. Suddenly, an alarm goes off. A critical life support system is failing. Now, Mission Control is there to help, but their message takes 20 minutes to reach you, and your reply takes another 20 minutes to get back. In that 40-minute communications gap, the spacecraft's AI has to be your expert engineer. That right there is the high-stakes problem that's pushing us to build these truly autonomous systems.
So, here's our game plan. We'll kick things off with why deep space demands this kind of thinking. Then we'll dive into a big problem. What happens when these AI brains get too complicated? From there, we'll check out a new, smarter way to trim them down, see how it actually performed in a test, and wrap up with why this matters for all of us, not just astronauts. Let's jump in. To solve problems when you're millions of miles from the nearest help, a spacecraft needs to do more than just follow a script. It needs to actually think, to reason through what's going wrong. And the foundation for all of that reasoning is something that sounds like it's straight out of science fiction, a perfect virtual copy of the ship itself. It's called a digital twin. A digital twin? Yeah, it's not just some static 3D model. No way. Think of it as a living, breathing simulation that perfectly mirrors the real spacecraft, and it's constantly being updated with real-time sensor data. It's the AI's personal sandbox for figuring stuff out. But, and this is the key, a digital twin is only as smart as the brain that's running it. And that brain is something called a Bayesian network. Okay, don't worry about the jargon, just think of it as a map of cause and effect. It asks questions like, if this valve fails, what's the chance that pump will overheat? It lets the AI connect the dots and make educated guesses, with uncertainty, just like a human expert would. So, when a sensor suddenly flags an issue, let's say a high temperature reading, the AI just snaps into action with this three-step process. First, it notices the problem. Then, its Bayesian network brain lights up, calculating the odds of every possible cause. And finally, bam! It zeroes in on the most likely culprit and updates its own understanding. It's just this constant, super-fast cycle of see, think, and adapt. But of course, there's a catch, and it's a big one. The more accurate and detailed you make this cause and effect map, the more power it needs, and the slower it gets. And I'm not talking about a little slowdown. This isn't linear. The complexity grows exponentially. That means a network that's just twice as detailed might take 100 or even 1,000 times longer to give you an answer. In an emergency, that's time you absolutely do not have.
So you end up with this awful trade-off, right? You're stuck. You can have a simple AI that's really fast, but, well, it's kind of dumb and might miss the real problem. Or you can have a genius-level AI that's super accurate, but takes forever to think. Neither of those is a good choice when lives are on the line.
So the logical question becomes, can we have the best of both worlds? Can we take that super smart, complex network and just trim it down, make it leaner and meaner, but without losing the intelligence? Well, yeah, and that process is called pruning. Now, the old way of doing this was purely mathematical. It uses a tool that basically measures how much information you lose every time you snip a connection in the network. So the algorithm just goes through and automatically snips the parts that seem the least important statistically. But as the researchers point out here, this method is totally blind. It's missing a crucial ingredient: real-world, expert knowledge.
And this is the fatal flaw. A purely stats-based pruner might see a failure that only happens, say, 0.01% of the time, like a micrometeoroid strike, and think, that's not important, snip. But a human engineer would be screaming, whoa, no, that might be rare, but it's mission critical if it happens. The algorithm just doesn't have that kind of judgment. And this is where the new research really shines. The whole goal was to create a way to prune the network that doesn't just look at the raw numbers, but also understands the wisdom of an experienced mission controller. The idea is just so elegant and practical. They didn't get rid of the powerful statistical tools. Instead, they decided to supercharge them by teaching them to think a little bit more like a human expert. So they did this by adding 3 new criteria. First up is observability, which basically asks, can we actually see this part with our sensors, or are we just guessing?
Second is knowledge. How sure are the engineers that this cause actually leads to that effect? And third, probably the most important, is utility. If this part breaks, how catastrophic is it for the mission? It's a fantastic way to turn an expert's gut feeling into hard data the AI can actually use.
Okay, so it's a great idea in theory, but does it actually work in practice? Well, the researchers set up a head-to-head competition to see which pruning method was really the smartest.
So here are our two contenders. In one corner, you have the baseline method, which uses nothing but cold, hard statistics. And in the other corner, you have the new proposed method, which combines those same stats with that expert knowledge we just talked about: observability, knowledge, and utility. And here's how they tested them. They started by building a perfect ground truth network, basically the answer key. Then they made a messy, overly complicated copy and let both the old method and the new method try to prune it down. Once they each had their new, smaller AI brains, they started throwing problems at them and measured how close their answers were to the perfect network, a real test of who was smarter. So, after this digital battle, who came out on top? Well, the results aren't just interesting, they have some pretty huge implications for how we should be building complex AI from now on.
This chart pretty much says it all. The proposed method is the higher bar. And as you can see, it didn't matter how much they trimmed the network, whether it was a little or a lot, the new method with the expert knowledge was consistently more accurate. I mean, it wasn't even close.
So the big takeaway here is that by adding that layer of human judgment, the AI got much, much better at knowing what information was important and what was just noise. It created a brain that was not only faster and more efficient, but fundamentally more reliable and, frankly, more intelligent.
And this is why this research is so important. It's not just about spaceships. This is a blueprint for building smarter AI across the board. Think about managing our power grids, or financial markets, or even AI systems that help doctors with diagnoses. In any field where an AI has to make a critical call, this idea of blending raw data with expert wisdom could be a complete game changer.
It really leaves us with a powerful final thought. We're getting unbelievably good at making machines that can calculate things at lightning speed. But what this research shows is that the real challenge and the real opportunity is in building machines that can exercise judgment. So the question we're left with is, what's the next frontier for embedding that kind of human-like wisdom into our machines?